In this lecture, we're going to do a few more involved area of triangle problems. In particular, we're going to apply that area formula that we talked about in the last lecture to shapes that aren't triangles. So let's remind ourselves what the area of the triangle formula is. So if you've got an angle, gamma, doesn't really matter where the angle is, and two sides, A and B, again, doesn't really matter where the sides are as long as the angle that you know is in between the two sides that you know. So you know two sides and the included angle. And the area of the triangle is 1/2 AB sine of gamma. So in this problem, we're told that a rhombus has sides of length 18 centimeters, and one of the angles is 128 degrees. Find the area of the rhombus. All right, so remember rhombus is quadrilateral, 4 equal sides. So in this one, we're told that each side is 18, and one angle measures 128. Well, if I draw that diagonal here, I see a triangle, and in fact, since I know a rhombus is also a parallelogram, I know that other angle is 128 degrees, and since a rhombus, all 4 sides are congruent, I know the other 2 sides also have a measure of 18 centimeters. So I have 2 identical triangles, so once I figure out the area of one of them, I just need to double it to find out the area for the other. So in this case, the area of the rhombus will be what? Well, we just said it was 2 times the area of one of the triangles. One of the triangles will have an area of 18 times the sine of 128 degrees. Notice in this case the 2 and the 1/2 will cancel, so I just need to multiply the 18s together and then the sine of 128 degrees. So we get approximately 255.3155 square centimeters. So again, notice that even though we had a shape that was not a triangle, we were able to still use the area of the formula for the triangle to be able to figure out the area for this particular polygon. All right, so let's do another application where we have the area of a regular polygon. In this case, we have a hexagon. We have 6 sides. So regular again means that all of the sides are congruent and all the angles are congruent. Okay. All right, so in this particular example, since the perimeter is 30, we know that if I call one of these sides length S, I know that the length of side S will be 30 divided by 6. I've got 6 sides, and I know they all have to be equal. The perimeter is the distance all the way around. So that side length S will be 5 inches. So each of these will be 5 all the way around. All right. So I know one of the sides. Pardon me. We also know some other things about polygons. Probably the easiest thing that we can notice is that if I put the center right here, then I know that I've got 6 congruent triangles in this particular case, because I can go from the center out, and I know that all of these distances all have to be the same. So really our goal here is to figure out one of the areas of one of the triangles, and then just multiply it by 6 to figure out the area of the whole thing. Okay. Also, we know that, imagine standing here at this point. If I spin all the way around that point, I go 360 degrees. So I've divided 360 degrees into 6 pieces. So I know that each of these angles here is 60 degrees. This is helpful information. In particular, it's helpful information because if I imagine now dropping this down to the other side, I know that we just said that these two sides are congruent, which means that this is an isosceles triangle, which means that if I drop the perpendicular down here, I know that I split this to a 30 and this to a 30. And since this is a right angle here, I know that this is 60. And of course, this is also 60. All right, in particular, we now notice that we've got a 60, 60, 60 big triangle, which means that's equilateral. So we know that the length of each of these sides is also 5. So just to draw this off to the side now, I've got a triangle that has a length of 5 on each side and a 60-degree angle at each angle. Well, that makes life a little bit easier to figure out the area of this particular triangle, because now I know two sides in the included angle, right? So the area of one of these triangles is going to be 1/2 times 5 times 5 times the sine of 60 degrees. And even though I could pull out my calculator, I know that we know the exact value for sine of 60 degrees. That's square root of 3 over 2. So I can actually write this as 25 square root of 3 over 4. Pardon me. Now remember, this is, and this will also be square inches. This is one triangle, right? And we just said that this hexagon was made up of 6 of these triangles. So the area of your hexagon will be 6 times the 25 root 3 over 4, which gives you, what, 75 square root of 3 over 2 square inches? And if you really, really, really want to convert that to a decimal approximation, you can type that into your calculator, and this is approximately 64.9519 square inches. But notice the process that we did. And this process is going to pop up in other applications that we're going to do here in a minute with other regular polygons. The first thing I noticed is that I divided this polygon up into 6, in this case 6 congruent triangles, and then found the area of one of those triangles by using the fact that I knew these base angles because I knew this vertex angle up there, and then went from there. Now, in this case, we were lucky that we had an equilateral triangle to start with. In other ones, we won't have equilateral triangles. We'll have to do a little bit more work to figure out the length of the side. So let's do one of those. Let's see, what kind of a shape do we have here? 1, 2, 3, 4, 5, 6, 7. This is a heptagon. This is 7 sides. But the process is going to be the same. I'm going to put in the center, and I'm going to make a triangle. Okay? Now, like we mentioned, I'm not going to draw all the triangles in here because it gets messy, but we just mentioned before that all the way around is 360 degrees. So this angle right in here, it has to be a 1/7 of that. So that angle right in there has to be 360 divided by 7. And if I use my calculator for that, 360 divided by 7 gives me about 51.4286 degrees, about. That means I can figure out these other two angles at the bottom, okay? Because I know that this is an isosceles triangle. Those two lengths are the same, which means that these two angles are the same. And we know that the sum of the angles has to add up to 180 degrees. So if I want one of these, let me just call it alpha. This would also have to be alpha, so that we know that alpha will have to be what? 180 minus the 51.4286. Now that's going to be both of them together, so I have to divide that by 2. The 180 minus the 51 and change is what's left over, and we divide it in half because those two angles are equal. So if I do 180 minus that 51.4286 number, and then divide that by 2, we get approximately 64.2857 degrees. So that's the measure of one of these angles. All right. Not necessarily pretty numbers, but that's the idea here. Whatever's left over out of the 180, you're going to divide it in half to get each of those particular angles. All right. We also have information about at least one of the sides here. The perimeter is 35. So if I call this S, remember there's 7 sides here, so the S will be that 35 over 7, or 5 miles in this case. It's one very, very large heptagon. Okay. I still don't know another side. I now know the length of one side, and I know an angle. Actually, I know all 3 angles. If I can figure out one more side, I can figure out the area of the triangle. Well, I know I have a side and its angle opposite. I know those 2 things. I have an angle. I can figure out the side opposite. So let's just call this R, for lack of a better letter. We know that the sine of the alpha, which was 64.2857 degrees, over R, will be equal to the sine of the 51.4286 degrees, and that'll be over 5. And we can solve this for R, right? We cross multiply and then divide by this number. So it's 5 sine of 64.2857 degrees over the sine of 51.4286 degrees. So let's see that. We're going to need 5 times the sine of the 64 number, and then divide by the sine of the other number, the 51.4 whatever number. And this gives us about 5.7619 miles. All right, so now I know 2 sides and an included angle. So the area will be 1/2 times 5 times the 5.7619 times the sine of the 64.2857. Now let's think about where all those numbers came from. 5 is this side. 5.7619 is this side. And the 64.2857 is that angle. Okay. 1/2 times the 2 sides times the included angle. So let's do that. So 1/2 times 5 times the included angle, and then I need the multiply that by the sine of the 64.2857, and we get approximately 12.9783. This would be square miles. And now remember, this is one of the triangles, right? It's not the whole thing. So to get the whole area of the heptagon, I have to take 7 times that area. So the area of the heptagon now will be 7 times the 12.9783 number, which is about, let's see, 90.8478 square miles. Oops, not square minutes, square miles. But notice, even though the numbers were uglier, the process was the same here, right? We divided the 360 by the number of sides, right? We divided the 360 by the number of sides to get this angle up here. Used our knowledge of how the angles have to add up in a triangle to get these angles down here. We used the law of sines, previous information, right? Previous test to figure out this side here. And then used our area formula to get the area of the triangle, and then finally just multiplied by how many triangles we have. All right. Let's talk about this last application problem, a little bit more complicated, but it's the last one here. So, Pentagon in Washington, D.C. is built in the shape of a regular pentagon. Each side of the Pentagon has a 921-foot wall. And then the building inside of that has a pentagonal courtyard, okay, with the same center. And then each wall of the center of the courtyard has a length of 356. So what's the area of the roof of the Pentagon? All right, this one sounds like a fun problem. All right, so we've got one big Pentagon. That is an ugly looking regular Pentagon, of course, because I can't draw. And then inside of that, we have another Pentagon. And if you've seen pictures of the Pentagon building in DC, this is what it looks like. Now, roughly what it looks like. All right, so what they're asking us to figure out is this roof area, this part that I'm putting in green here. That's what we need to figure out the area of. So what's our plan of attack going to be? Well, I want to figure out the area of the big Pentagon and then subtract out the area of the small Pentagon. But talking about, going back to what we just talked about in the previous two examples, the process for each of those pentagons is going to be the same. The only thing that's going to change, really, is the length of one side. So they tell us that the outer wall is 291 and that the inner wall is 356. But other than that, the process is exactly going to be the same for both of these. So let's first start with the big Pentagon here. Let's say we have a 921 here. I again make my triangle in the center, from the center, pardon me. I just need one of these triangles. We find this angle in here by taking the 360 and dividing by the number of triangles there are. That looks like that's 72 degrees up there. Okay. So then if I want to figure out, like we mentioned in the last problem, if I want to figure out each of those alphas, the alpha will be 180 minus the 72. That's what's left over from that one angle, and we have to divide it in half to split for each of these angles, because again, this is going to be an isosceles triangle. And in this case, you'll get 54. Okay. So we now know all three angles, and we know one side is 921. So we need to figure out another side so that we can figure out the length of this side. So we have two sides and an included angle. So much like the last problem, we'll do law of sines. Sine of 72 degrees over 921 is equal to the sine of 54 degrees over, I'll call it R again for lack of a better letter. Notice I'm using law of sines. Angle, opposite side, angle, opposite side. Solving for R here again, multiply, cross multiply, and then divide by that sine of 72. So we'll have 921 sine of 54 over sine of 72. And that gives us what? So if I do 921 times sine of 54 divided by sine of 72, we get approximately 783.4494, and that's feet, because the 921 was given to us in feet. So now I need the area of that one triangle. So I do 1/2 times the 921 times that 783 number times the sine of 54, because I'm using this, let me put it in red here, this side, this angle. So if I do that, if I do 1/2 times 921 times that 783 number times the sine of 54, we get, go back to black here, 291,875.8942 square feet. Now that's just for one triangle. right? So the area of the Pentagon then, I'll say it's the big Pentagon because we still have to do the little one, will be 5 times that. So I take that number and multiply it by 5, and we get 1,459,379.471 square feet. That's just for the big Pentagon, right? Okay. We need to subtract out the area of the little Pentagon. Remember, we're going for the area of the roof, or area of the floor. It doesn't matter. It should be the same, roughly. So we, if you don't account for the walls, they should be the same. We found the big area. We still need to find the small area and subtract. But notice for this small one, I'm not going to draw a new picture for this. Notice for the small one, we still get the same computations. This is still going to be a 72-degree angle. This is still going to be a 54-degree angle. So the only thing that's going to change is what this little r is up here. It's going to be the same computations for the angles. The only thing that's going to change is how we find that little r, but this is going to be the same formula. We're just going to change one number in it. So we're going to use this law of sines again. We know the sine of 72 degrees, this time over 356, because that's the opposite side, is equal to the sine of 54 degrees over the little r. Cross multiply, divide by that sine of 72. We get 356 sine of 54 over sine of 72, which is approximately what here? So we need 356 sine of 54 divided by sine of 72. Gives us 302.8317, and this is feet. So now I have two sides and an included angle. So the area of one of the triangles is going to be 1/2 times that 356 times that 302 number times the sine of 54 degrees. And again, we're using this side, and this angle. You can pick any two sides and included angle you want. Just make sure you have two sides and the angle between them. That's why we're using the 54 and not the 72 here. Use calculator, so 0.5 times the 356 times the 302 number times the sine of 54. We get 43,609.2848. That's square feet. That's one triangle. So the area of the small pentagon will be 5 times that number. So multiply that number by 5 and we get 218,046.4238 square feet. And now we have the area of the big and we have the area of the small. So the area of the roof will be the 1459379.471 minus the 218.46, and then 42, and I'll round it to 4 in this case. So if we subtract the 1459379.471 and that 218 number, we get 1241333.047 square feet. This is a fairly easy number to check to see if it's plausible because the square footage of the Pentagon is a known number. You can go Google it and find out what that number is. So if you're really, really interested in knowing if that number, that 1.24 million square feet is a plausible number for the square footage of the roof, you should go check the square footage of the Pentagon. Remember, you're would be looking for the square footage of one floor, and I think the square footage is usually given to you by all the floors that it has. So, anyway, This gives you some more application types of problems that you'll be expected to do as far as area of triangle goes. Your quiz over this will open up at 11 o'clock on Monday. So 11 o'clock on the 20th, 11 a.m. It'll be due by 5 p.m. on Wednesday, the 22nd, and I will send an email out with all of this information as well. But just to let you know, that's what's coming up. And just like before, when you have take-home quizzes, I will be available during that Wednesday, 10 o'clock time if you've got questions. And I will also be available during our 10 o'clock time, usual 10 o'clock time on Monday, if you've got any questions about the previous video that I posted or this newest video that I just did. And you all should also know that I've also posted an additional practice problem sheet on Moodle with solutions. So you've got the practice problems on Moodle. I've posted this lecture without the solutions in it on Moodle so you can follow along. I believe I also emailed that out to everybody. So you've got lots of example problems on this, plus you'll have problems in Hawks to work on over this material. But this is pretty much it. Like I said, for this particular lecture, there was just the one formula and then doing a bunch of example formulas based on that formula. So we will talk to everyone later. Have a good one.